Carbon capture and sequestration, or CCS, has emerged as a pivotal technology in the fight against climate change. Highlighted by the IPCC as a critical tool, CCS offers the immediate opportunity to mitigate carbon dioxide emissions from industrial sources and fossil fuel power plants. While society's dependence on fossil fuels remains high, and sustainable alternatives are not yet universally accessible, CCS stands out as a practical solution for the near term. This video will guide you through the technical and economic landscape of CCS, explore real-world case studies, and discuss the policy shifts that could shape its future. Let's begin by understanding why CCS matters now more than ever. Power generation and industrial sectors are responsible for nearly 2,600 million metric tons of carbon dioxide emissions in the United States alone. This massive output is a key reason why scientists warn that our planet is on a path to dangerous warming. While renewable energy sources are growing, complete transition away from fossil fuels will take time. CCS provides a bridge, allowing us to reduce emissions now while cleaner technologies are developed and deployed. By capturing and storing carbon dioxide underground, CCS helps buy time in the urgent race to limit global warming. At its core, CCS is a series of technologies that capture carbon dioxide from large stationary sources, such as power plants and industrial facilities. The captured gas is compressed and transported, usually by pipeline, to a suitable underground site. There, it's injected deep below the surface into porous rock formations, safely trapped beneath impermeable layers that prevent it from escaping. This process not only reduces emissions but also leverages existing infrastructure, making it a practical option for immediate climate action. Put things in perspective, if CCS were applied to a 500 MW coal-fired power plant, it could capture 3 million tons of carbon dioxide per year. That's equivalent to the carbon absorbed by over 62 million trees or the emissions from more than 300,000 American homes. When stored underground at high pressure and temperature, the volume of carbon dioxide shrinks dramatically, making storage feasible on a large scale. These numbers highlight the significant potential of CCS to make a real impact on emissions. There are three main types of carbon capture: post-combustion, pre-combustion, and oxy-fuel combustion. Post-combustion capture is the most common, trapping CO2 after fossil fuels are burned. Pre-combustion involves converting fuels into a gas mixture, then separating out the CO2. Oxy-fuel combustion burns fuels in pure oxygen, producing a stream of CO2 and water that's easy to separate. An emerging fourth method, direct air capture, pulls CO2 straight from the atmosphere, though it's still in early development and currently more expensive. Direct air capture (DAC) is a promising technology that captures carbon dioxide directly from the atmosphere, independent of industrial sources. There are two main types: liquid DAC, which uses chemical solutions, and solid DAC, which uses sorbent filters. While DAC is still in the demonstration phase and more energy-intensive than other methods, costs are expected to fall as the technology matures. Large-scale DAC projects are already in the pipeline, signaling its potential role in future climate strategies. Once carbon dioxide is captured, it needs to be transported to storage sites. The most common method is via pipelines, which move CO2 in a supercritical state, meaning it behaves like both a liquid and a gas. The United States already has over 4,500 miles of CO2 pipelines, capable of moving about 68 million tons annually. Repurposing existing natural gas infrastructure could further expand this network, making large-scale CCS deployment more feasible. Injecting CO2 underground for permanent storage is regulated under the EPA's Underground Injection Control (UIC) program. There are 6 classes of wells, but Class VI wells are specifically designed for geologic sequestration of carbon dioxide. These wells are engineered to protect drinking water sources and ensure that CO2 remains securely stored deep underground, minimizing environmental risks. For effective sequestration, CO2 must be injected at least 800 meters underground, where it stays in a supercritical state. The storage formation must be porous and permeable, overlaid by an impermeable caprock to prevent upward migration. There are several trapping mechanisms: buoyant trapping, residual trapping, solubility trapping, and mineralization. Buoyant and residual trapping are the most significant, with the latter offering the largest storage potential in the United States. Typical CCS system involves an emissions facility such as a power plant where CO2 is captured. The gas is then transported via pipelines to injection wells, where it is sequestered deep underground. This integrated approach ensures that emissions are not only captured but also securely stored, reducing their impact on the atmosphere. Economics of CCS are complex, with capture costs representing the largest share of total project expenses. These costs depend on the purity of the CO2 stream and the number of exhaust streams at a facility. For example, bioethanol plants have nearly pure CO2 emissions and thus very low capture costs, while natural gas power plants face higher costs due to lower CO2 concentrations and more complex exhaust stream. Capture costs can vary widely, not just between sectors but even within the same industry. Factors such as facility age, annual emissions, and energy costs all play a role. For some sectors like cement and steel, the uncertainty is especially high. This variability makes it challenging to predict the exact economics of CCS projects and highlights the need for flexible policy support. Good news is that capture costs are falling, especially in the power sector. For example, costs dropped from $110 per ton in 2014 to $65 per ton just 3 years later, and are projected to fall further to $45 per ton by 2025-2027. This trend mirrors cost reductions seen in other renewables like wind and solar, suggesting that CCS could become more affordable with continued investment and scale. Transporting CO2 via pipelines is the most cost-effective method for large-scale CCS. Pipeline costs depend on the distance and the annual volume transported. Larger projects benefit from economies of scale, with cost per ton decreasing as volume increases. For example, transporting 3 million tons per year costs more per ton than moving 30 million tons annually over the same distance. Sequestration costs include site preparation, drilling, monitoring, and maintenance. Costs are generally lower for depleted oil and gas reservoirs, where more is known about the geology compared to saline reservoirs. Offshore projects are more expensive due to higher risks and operational complexity. These factors must be considered when planning CCS projects. To encourage CCS adoption, the U.S. government offers the 45Q tax credit. This incentive provides up to $50 per ton of CO2 sequestered in geologic formations and $35 per ton for enhanced oil recovery. While the credit has spurred some investment, experts argue that higher incentives, up to $85 or even $175 per ton, may be needed to make CCS widely economical across more sectors. Analyze CCS potential. Researchers reviewed technical and economic literature, mapped industrial emission sources, and assessed storage capacity in major U.S. sedimentary basins. 4 case studies were developed to model project costs for different emission sources and transport distances. These studies help illustrate the real-world challenges and opportunities for CCS deployment. 4 case studies focus on different sectors and regions: bioethanol emissions in the upper Midwest, ammonia and hydrogen in the Gulf Coast, coal power plants in Colorado and Wyoming, and natural gas power plants in the same region. Each study examines the economics, storage potential, and policy implications for CCS in these contexts. Project costs for CCS vary by sector. For example, bioethanol, ammonia, lime, and natural gas processing can be economically viable at current tax credit levels, especially for projects with low capture costs. However, sectors like hydrogen, iron and steel, coal, and natural gas power plants face higher costs and greater uncertainty, making them less attractive without additional policy support. Raising the 45Q tax credit to $85 per ton would make CCS projects for bioethanol, ammonia, lime, and natural gas processing fully economical. However, even at this higher level, sectors like coal and natural gas power generation would still struggle to break even. Only a further increase to $175 per ton would make all sectors and cost scenarios viable, highlighting the importance of policy in driving CCS adoption. If capture costs fall by 60% over the next decade, as seen in other renewables, CCS could become attractive even at current tax credit levels. This would open the door for broader adoption across more industries, especially if policy incentives keep pace with technological improvements. In 2020, power plants accounted for 58% of U.S. industrial CO2 emissions, followed by petroleum and natural gas systems at 12%. Other sectors, including chemicals, minerals, metals, and pulp and paper, make up the rest. Understanding where emissions come from helps target CCS efforts for maximum impact. Capture costs vary widely by sector. For example, bioethanol facilities have the lowest costs, while natural gas power plants have some of the highest. The percentage of total emissions also varies, with power plants offering the largest opportunity for emissions reduction but at a higher cost and uncertainty. Emission sources are not evenly distributed across the country. For example, bioethanol plants are concentrated in the Midwest, often far from major sedimentary basins, requiring long pipelines for sequestration. In contrast, ammonia, hydrogen, and cement plants are often located near suitable storage sites, making CCS more feasible for these sectors. The United States has enormous storage potential for CO2 in its sedimentary basins. Estimates suggest enough capacity to store over 1,000 years' worth of current annual emissions. This abundance of space means that, from a storage perspective, CCS is not limited by geology but by economics and policy. Among U.S. sedimentary basins, the Gulf Coast Basin stands out for its massive storage potential, followed by the North Slope of Alaska, South Florida, Illinois, Williston, Anadarko, and Permian basins. These regions are prime candidates for large-scale CCS projects, especially where emissions sources are nearby. First case study examines capturing bioethanol emissions from facilities in Iowa, Minnesota, Nebraska, North Dakota, and South Dakota, and transporting them to the Williston Basin for sequestration. The project, modeled after the Summit Carbon Solutions proposal, aims to capture up to 12 million tons of CO2 per year, equivalent to removing emissions from 2.6 million vehicles. The main challenge is the high cost of long-distance pipeline transport. Williston Basin offers several prospective formations for CO2 storage, including the Madison Formation, which stands out for its high thickness and porosity. With a mean storage potential of over 18,000 million tons, the Madison Formation can easily accommodate the emissions from the bioethanol facilities targeted in this case study. Second case study focuses on capturing emissions from ammonia and hydrogen plants along the Louisiana Gulf Coast. These facilities produce nearly pure CO2 streams, making capture costs low. The proximity to the Gulf Coast Basin with its vast storage potential makes this region ideal for CCS deployment with relatively short transport distances. The Gulf Coast Basin contains several geologic formations suitable for CO2 storage, with high porosity and permeability. These characteristics, combined with the region's industrial activity, make it a strategic hub for large-scale CCS projects targeting ammonia and hydrogen emissions. Third case study examines capturing emissions from coal-fired power plants in the DJ Basin, covering eastern Colorado and southeast Wyoming. These plants have higher capture costs due to lower CO2 purity and more complex exhaust streams. However, the proximity to suitable storage formations helps reduce transport costs. The DJ Basin offers several formations with significant storage capacity for CO2. While capture costs are higher for coal plants, the availability of nearby storage sites makes CCS more feasible here than in regions lacking suitable geology. Fourth case study swaps coal-fired power plants for natural gas combined cycle plants in the DJ Basin. While natural gas plants emit less CO2 per unit of energy, their capture costs are even higher due to lower CO2 concentrations. This scenario tests the economics of CCS as the power sector shifts away from coal. Across all four case studies, the economics of CCS depend heavily on capture costs, transport distances, and the value of policy incentives. Bioethanol and ammonia projects are most viable under current tax credits, while coal and natural gas power projects require higher subsidies or further cost reductions to be competitive. Analysis suggests that increasing the 45Q tax credit to $85 per ton would make CCS viable for a broader range of industries, especially those with low capture costs. For sectors with higher costs, further technological improvements or even higher incentives will be necessary. Policy refinement is essential to unlock the full potential of CCS. CCS is especially important for industrial sectors like cement, steel, ammonia, and bioethanol, where there are few viable alternatives for deep decarbonization. By capturing and storing emissions from these processes, CCS can play a key role in reducing industrial carbon footprints. For the power sector, CCS can serve as a bridge technology, reducing emissions from existing fossil fuel plants while renewables and storage solutions scale up. However, the economics are challenging, and in some cases, a full transition to renewables may be more cost-effective than retrofitting plants with CCS. Ensuring the long-term security of stored CO2 is critical. Monitoring technologies and regulatory frameworks are in place to track injected CO2 and detect any potential leaks. This oversight helps build public trust and ensures that CCS delivers real climate benefits. Implementing CCS projects involves navigating a complex web of administrative policies, permitting processes, and state-federal coordination. Streamlining these processes can help accelerate CCS deployment and reduce project costs. Technologies like enhanced oil recovery (EOR) have been injecting CO2 underground for decades, providing valuable experience for CCS. Lessons from EOR and natural gas storage can inform best practices for safe and effective CO2 sequestration. Several Class VI injection well projects are underway in the United States, demonstrating the technical feasibility of large-scale CO2 sequestration. These projects provide important data and help refine regulatory frameworks for future CCS expansion. Despite its promise, CCS faces challenges including high upfront costs, regulatory hurdles, and public acceptance. Continued research, policy support, and transparent communication are needed to overcome these barriers and realize the full potential of CCS. Innovation in capture technologies, transport infrastructure, and storage monitoring can drive down costs and improve CCS performance. As more projects are deployed, learning by doing will accelerate improvements and help CCS scale up. While this review focuses on the United States, CCS is a global technology with projects underway in Europe, Asia, and beyond. International collaboration and knowledge sharing can help accelerate CCS adoption worldwide and contribute to global climate goals. CCS is not a silver bullet, but it is a vital part of the climate solution toolkit. With abundant storage potential, falling costs, and supportive policies, CCS can help bridge the gap as we transition to a low-carbon future. Continued investment, innovation, and policy refinement will be essential to unlock its full potential and ensure a sustainable path forward.